So today we'll be talking about Turing machines and their relation to algorithms, or in other words, a Turing machine as a definition of an algorithm. So last time we introduced Turing machines, and we gave a high-level description of a Turing machine that recognizes what language? What was the language for which we gave a high-level description of a Turing machine? So it was this language. So we just gave a high-level description of a Turing machine that recognizes this. Now let's try to review the basics of a Turing machine and how it differs from finite state machines and push-down, or finite state automata and push-down automata. So what are the features in the Turing machine that make it more powerful than finite automata and push-down automata? Yes? Okay, so the push-down automata, a push-down automaton has memory, but what's the difference between the memory in a Turing machine and the memory in a push-down automaton? Oh, yeah, so the memory in a Turing machine, you can go left or right, and it's just general. It's a linear memory, piece of memory that has no bounds, right? What are the limitations on the push-down automaton? What are the limitations of memory on the push-down automaton? It's a stack. So you're limited to a stack, and you're limited to stack operations. Anything that you can do with a stack, you can do it with a push-down automaton. If the stack is good enough, you can do it with a push-down automaton. If the stack is not good enough, then you cannot do it with a push-down automaton. And for this language, for example, the stack is not good enough. The stack was good enough for this language, this related language, WWR, because the stack is good for matching 101 with 101. So this, let's take another. So you have 110, 110. So this language. So this is W. This is WR. This is something that you can do with a stack, because you push this, then you push this, then you push this, and when you pop, the last thing that you pop, the first thing that you pop is the last thing that you pushed. So the stack is good for recognizing this language. This would be the top of the stack. It's like let's change the alphabet. So let's do it. So on your stack, you will push the 0, then you'll push the 1, then you'll push the 2. Then when you pop the 2. And that's why the stack is good for recognizing this, but the stack is not good for recognizing this. You'll need a more general type of memory. And this is something that we showed with a high-level description, how to do with a Turing machine. So the Turing machine has unbounded memory, and it can go left or right. And the fact that it can go left or right gives it more power, but also introduces a complexity. What's that complexity that gets introduced by the feature of moving left and right? What does that introduce? Being able to move left or right.
You can remember where you were.
No, you can do marking, and you can remember where you were, but by moving left and right, you can process a string multiple times. And what's the consequence of that? Yeah, you may not terminate. So termination is an issue. On Turing machines, termination is an issue. Will it terminate or not? Not all Turing machines terminate on all inputs. And that's why for a Turing machine, the outcomes, the possible outcomes are accept, reject, or loop. Loop forever. Now, if for a given language, for a given language there is a Turing machine that will either accept or reject but never loop, what do we call this Turing machine? Yeah, so it's a decider for this language. So if there is if for a given language there is a Turing machine that will either accept or reject any string, so for every string the result is going to be either accept or reject, and the result will never be looping forever, then in this case we say that this Turing machine decides the language. Okay, so this is what we mean by deciding a language. So in that case we say that the language is Turing decidable. While if for a given language there is a Turing machine that will accept every string that belongs to the language, but if the string does not belong to the language, it will either reject or loop forever. In that case, what do we say? What does the Turing machine do in that case for that language? If for any given string, if it belongs to the language, it's going to accept. If it doesn't belong to the language, it will either reject or loop forever.
Recognizable?
Yeah, in that case, we say that the language is recognizable by a Turing machine, or the Turing machine recognizes the language. So recognizing means accepting every string that belongs to the language. But if the string doesn't belong to the language, we will either reject or loop forever. While deciding is something that will give you a more definite answer within finite time. Not a more definite, but a definite answer. So if the Turing machine gives you a definite answer within a finite period of time, that's deciding a language. Okay. And we gave that hierarchy last time. We have the simplest languages are regular languages. The larger set is context-free languages. And then the languages that are Turing decidable are here. And the languages that are Turing recognizable is a larger set of languages. Turing decidable or Turing recognizable. Okay, so this is like just a review of the main concepts that we introduced last time. Now, Turing machines are interesting because they are a theoretical model for an algorithm. So any, it has been hypothesized that a Turing machine, any computation that can be done by computers, can be performed by some Turing machine. And this is what we call the Turing thesis. Which was proposed in 1936. Any computation that can be carried out by mechanical means can be performed by a Turing machine. So it's saying that a Turing machine is general enough to do anything that a computer can do. So at that time in 1936, computers were not that popular, and most people were not familiar with computers, and even people who introduced or who developed these concepts were mathematicians at the time. So when it says carried out by mechanical means, with our terminology, the translation is anything that can be done by a computer, or any problem that can be solved using a computer. So here, in this part of the course, we will be looking into problems that cannot be solved using computers because there is no algorithm for them that is guaranteed to terminate. So, or it's, they're not decidable by a computer. So there is no algorithm for this problem that is guaranteed to terminate. So, given this thesis, now this thesis has, all the evidence that we have supports this thesis. So it's nobody has come up with anything that a computer can do, but a Turing machine cannot. So anything that you can do with a computer. Now the Turing machine can do it in a primitive or an inefficient way. So we don't care about efficiency here. At this point, we are studying decidability or computability. So there is the concept of computability, studying whether a given problem is computable, can be computed, or can be performed by a computer or not. And there is complexity, which is studying whether there is an efficient algorithm or not. So in computability, we don't care if the algorithm is efficient or not. So we will be studying some inefficient algorithms, and we don't care when we study computability, because the question that we are trying to answer in computability is this computable by a computer, or is this something that can be done by a computer at all or not? And if we can find a terribly inefficient algorithm, that will still be fine from computability point of view. But from complexity point of view, complexity theory is the theory that is based on the asymptotic complexity analysis, or the big O notation that you are familiar with. The big O notation, that's complexity. That's where we care about complexities. That's where we look for efficient algorithms. And in fact, from a practical point of view, if there is an algorithm for solving a problem, but that algorithm is not efficient, sometimes an inefficient algorithm will be useless. More specifically, if you have an exponential algorithm for solving a problem, an exponential algorithm can take an unrealistically large amount of time to solve a problem. For example, for n equals 100, an exponential algorithm can take billions of years. Now, billions of years, from computability theory point of view, this is computable. So from computability theory, this is computable because a billion years or a billion years is a finite period of time. So this is computable. But is it efficient? No, definitely it's not efficient. And from a practical point of view, it's useless, because if it exceeds the amount of time that is considered reasonable for this, or that we can wait for this algorithm to terminate, at least we would like the algorithm to terminate in our lifetimes, right? If the algorithm terminates, after we die or after our grandchildren die, then if the computer, assuming that the computer stays then there and and it's the power there is still power and everything is continues to run for a billion years. Yeah, but it's not. It will eventually find the solution. But will the people who are interested in seeing that solution be still alive? That's another question. So from a practical point of view, an algorithm, a problem can be computable, but there is no efficient algorithm for it. So from a practical point of view, an inefficient algorithm can be useless. Anyway, so right now, this part of the course, basically we will be studying algorithms. Algorithms for computing certain problems, and we will just take it, we will assume that anything that we have an algorithm for, there is a Turing machine. It can be done by a Turing machine by, taking this, the Turing thesis, assuming that the Turing thesis is true, and that anything that we can have an algorithm for is something that we can be done using a Turing machine. So let's look into some problems about. In fact, we have to look into first introduce the idea of viewing a problem, an algorithmic problem that we would like to solve, as a string recognition problem. So this is an idea. This is an interesting idea. It's like, let me describe a simple algorithmic problem. So you have a graph, and you are given a graph, an undirected graph, and the question is this graph connected or not? Of course, we look at this instance and we can easily tell that this is not connected, because D is not connected to A, B, C. Now, in algorithms, what's the algorithm that can solve this problem for us? What algorithm can we use to check the connectivity of a graph, of an undirected graph, if it's connected or not? So in fact, we can use any traversal, any kind of traversal, right? So it's you start from, you pick any vertex, and then you do any traversal. In fact, it doesn't matter if it, for the sake of checking connectivity, you can do DFS or BFS, or even any traversal that is not DFS or BFS. Any kind of traversal that will basically find all the vertices that are reachable from this, and you just traverse and find all the vertices that are reachable from the vertex that you have picked. And then once you find all the vertices that are reachable, you scan all the vertices. If all of them have been reached, then the graph is connected. If there is at least one vertex that has not been reached, the graph is not connected. So in this case, you will reach B and C, but you will not reach D, so the graph is not connected. So this is a simple algorithmic problem. Now, how can we view this problem as a string recognition problem, or determining if a string belongs to a certain language? In fact, you can view it as a string recognition problem by viewing the graph as the graph encoding or representation as a string. Like if you write a program, you have your program that processes a graph, and the input to the program is a graph. And then this program is going to tell you, let's call it a connectivity program. Connectivity checking program. You input to this program a graph representation, and then it's going to tell you yes or no, if the graph is connected or not connected. Right? Now, this graph representation is going to be some kind of encoding of the graph. One possible encoding is, just list the vertices A, B, C, D, then list the edges. So I have edge AB, edge AC and edge BC. So these are the vertices. This is an encoding of the vertices, and this is an encoding of the edges. But what's this thing? This is a string, right? So in fact, the input of any program can be viewed as a string, right? If your program takes command line arguments, then that command line argument that you input to the program is a string, right? What you input at the command line is a string. If your program takes an input file like this, you put this graph encoding in an input file, the input file you can view it as a string of characters, right? Now, what about a program that has a graphical user interface? Can you still view that as a string? Yes, you can view it as a string because it's a string of commands, right? So you can come up with any kind of encoding for any command that you issue for a program with a graphical user interface. So what's a command? It's selecting a menu, right? So you can encode selecting this menu option with a certain symbol or clicking on something. So anything that you do, even in a graphical user interface, selecting something from a menu or clicking something on something with the mouse or whatever, you can encode this as a string. So you can view the input to any program as a string of symbols that encode something. Whether it's it's a graph or it's certain commands that you issue to a program with a graphical user interface or whatever. Okay, so now we understand that the input is a string and the output is yes, no. Now, how does this relate to string recognition? How can you view this problem as the problem of determining if a string belongs to a certain language? What's the language here? What's the formal language in this case that will make this problem, that will allow you to view this problem as a problem of checking whether a given string belongs to a certain language? What should the language be here? What's the language? How would you define the language?
Every vertex has to be in the edges, like it has to show up.
Okay. No, don't try to just say something about what it takes for a graph to be connected. The language here is just the language that consists of all encodings, all graph encodings that are connected. So the encoding of a connected graph is a string that belongs to this language. So this encoding does not belong to the language. So this is a reject. This is a reject. While this is an accept. A, B, C, A, B, A, C, B, C. A, B, C is a connected graph. So this encoding here is an encoding of the encoding of a graph, a connected graph. This is an accept. So this means that any algorithmic problem whose solution is yes or no, which is what we call a decision problem, problem whose solution is yes or no. Any problem, any algorithmic problem whose solution is yes, no, can be viewed as a string recognition problem or checking if a string belongs to a certain language or not. So the strings or the encodings for which the answer is yes belong to the language, and the strings for which the answer is no do not belong to the language. Okay? So do you see this this idea? Any questions on this? Yeah, so now that's why we can even though we can view the Turing machine as a machine that can recognize languages or decide languages, we can also view it as a machine that solves algorithmic problems, right? At least decision problems, the problems for which the answer is yes or no. Okay, so now let's look into a problem that has to do with, or in fact, this graph algorithm problem, we can formulate it as, this problem, language L, G, where G is an encoding of a graph. G is a connected, undirected graph. So it's the language that includes the set of strings that are encodings of graphs, and these graphs are connected, undirected graphs. So, and this is a language that's recognized by a Turing machine. Now, to describe a Turing machine for this language, so let's call it machine M. This Turing machine, we will use just a high-level description. So we will just say, we'll describe an algorithm as pseudocode, even on a higher level than the pseudocode. Just, we will give a high-level description of the algorithm. We'll just say, okay, select a vertex, any vertex. Any vertex, and mark it. Then step number 2, repeat until no more marking is possible. Repeat what? If vertex X is marked, mark all of its neighbors. Okay? And repeat this until no more marking is possible. And step number 3, scan all vertices. If there is an, or if all vertices are marked, accept, else reject. So what's this is just, we're not showing here a state diagram like we did for finite automata and push down automata, because a state diagram for this would be too complicated, too messy. We're only giving a high-level description. So this is a high-level description of an algorithm that will determine, given a graph, it will determine if this graph is connected or not. And these are the high-level descriptions that we will be using to describe Turing machines in this part of the course.